What's up, science nerds? This is my homemade ion optic system. It fires a collimated beam of electrons at such a high energy that even rocks start glowing. Building this took me a lot of research, development and straight up trial and error, all at an amateur level. By the end of this video, you know how to build an electron gun for various applications. I'll also show you how to simulate this kind of system to fine-tune their performance. We'll also dive into the oxide-coated cathode, a hot topic in the DIY vacuum tube scene. And at the end, we'll irradiate some stuff with electrons and explore some real-world application. Alright, what is cathodoluminescence? It's just a fancy word for when materials get hit by high-energy electrons and start glowing. Why? Because they get excited to a higher energy level and they release visible light as they chill out again. This technology is everywhere, from checking for defects in semiconductors to telling if your diamond is natural or lab-made. All of the best vintage instruments use in some way this kind of technology, from ancient cameras all the way to telescope. This here is an electron gun from an oscilloscope. Its job is creating and steering the electron beam that hits the fluorescent screen to produce light via cathodoluminescence. Our goal is to build something like this, but simpler and DIY friendly. In this electron gun you can see a lot of electrodes. Here on the right you have a cathode where electrons are made by hot filament. Then the anode, this larger cylinder, which extract them and partially accelerate them. Here you can see instead some focusing lenses, and then you have these two deflecting plates that steer the electron pen on the fluorescent screen. Our goal is to make a focusing system so that the generated electrons don't shoot in all directions like you usually have in a homemade electron gun jar that you see on the internet. So there are mainly two categories of focusing lenses. They are the electrostatic and the magnetic one. Inside the magnetic system type, there is a Lorentz force created by a magnetic field that changes the electron trajectory into a spiral and makes them cross each other's path somewhere at a specific focal distance. It needs active power to operate, and its simulation is more complicated than the other type of system, which is the electrostatic one, for example this electroscope, in which we use a fixed or variable potential that generates an electric field that causes Coulombic repulsion to physically move the electrons closer or farther apart from each other. It is used inside the oscilloscope like this one because they have an advantage of the higher refresh rate. We are going to use mainly this type of system because it can be operated using a fixed potential generator and can also be calculated. So now that we know the basics, let's see the design I created. This is my electron gun. Its main body is a KF flange here that seals into a vacuum chamber using a rubber gasket. This rear part comes off from the main one, revealing another KF flange that is silver soldered to the copper body. Instead, here you have the cathode with another flange that supports the high voltage feed-through and the cathode itself. The cathode is a hot type having a functionalized filament to lower the work function, but we'll discuss in more detail that later. For now, we only need to know that it emits electrons due to the thermionic effect, like any other vacuum tube. The cathode is at a lower potential of several kilowatts from ground, and so as soon as the electrons are emitted, they are repelled away from it towards the screen. Here comes into play the electrostatic lens. I used an Hensel lens which has 3 electrodes at different potential to focus the electrons. To keep things compact, the first electrode doubles as both the extraction electrode and the first lens electrode. My ionic lens system then uses a central electrode, this one, that is at a lower potential compared to the neighboring one, so that when the electrons are accelerated away from the cathode, they enter a region of negative electric field, which forces the divergent electron to get slowed down and to be subject to a radial compression force that impresses them with a radial momentum towards the central axis. This mechanism results in an inward bending of the trajectory of the electrons, which is proportional to the strength of the electric field generated by the central electrode, which in turn depends only on his electrical potential. So by changing the voltage applied to this electrode, we decide how much and where the electron will be focused or collimated. The third electrode here is optional in my case because I have a metal vacuum chamber. Its purpose is only to make the electron regain their kinetic energy after being slowed down by the focusing electrode. To drive the central electrode, we need to bring the high voltage line inside of the vacuum chamber. For that I use this glass rod here on the side. They are embedded in this white epoxy resin, which is torsid, which serves as mechanical support for the extraction electrode, but also as vacuum sealant to prevent air intake from outside. The two glass rods exit here, where the conductors are connected to the high voltage power supply. The cathode contains also an electrical filter from behind here. That is the main brass rod, which is insulated from the smaller flange also by resin. To see where our electrons are going, I use some phosphor screen, like this one. They are similar to the one found in CRT TV. This is an example of it. The phosphor have been extracted from a fluorescent light bulb by dipping it in an ultrasonic water bath. The water suspension was then deposited on a conductive glass substrate like this ETO one, and then left to evaporate. So this is the image you can see produced by this electron gun here. You can see a very clear dot inside of the screen. This is an indication of the quality of the lens system. This image instead is the one produced on the phosphor screen by the first electron gun I designed and then realized. This is the electron gun itself. There are 4 brass rods that works as a conductor and support to power this cylindrical electrode here in the center. It is pretty shitty, as you can see. The reason is that I didn't consider the influence of the connecting rod on the electron trajectory. The reason for the bad quality of the image is that the electrons are bent from the electric field leakage of the connecting rod inside of the focusing lens zone. And so they are stretched in one direction and compressed in the other one, and this causes this star image to appear. Also in this electron gun I used a tungsten filament cathode extracted from an X-ray tube, but then I made the better version here, which works very well because I used a large cylindrical electrode, which minimizes their disalignment influence over the dot, and also minimizing the distance between the electrode reduced the electric field leakage from the connecting rod. Also you can see here I use this type of brass stuff with a glass rod to be able and adjust the height and the distance of the different electrodes from each other. But we are watching this video also to know how to design something like that. Well, this has taken a lot of work learning about ion optics, experimenting, and most fundamental, this has been done using some specialized software, which is CST Particle Studio. This is a finite integration technique electromagnetic simulator software that uses an interactive method to solve the integral form of the Maxwell equation, quantizing three-dimensional space using hexagonal or tetrahedral mesh, taking into account the electrostatic repulsion of the charge between themselves and evaluating the convergence of the simulation iteration. It is complicated but works pretty damn well. Using it, in fact, I produced a lot of this cool image you saw during the video, and I was also able to simulate my electron gun before building it. So I was able to optimize the geometrical parameter so that I could achieve the desired spot diameter of around 1 mm. Here you can see a cool simulation of the path of the electrons that they will take from their generation in the cathode to the screen. You can see that at the beginning they diverge outward, and then they reach the lens and get squeezed inward and are focalized at around 200 mm from the cathode. To vary the focalization, it is possible to change the potential on the central electrode. but I didn't want to make a high voltage power supply with two variable output. So instead I chose to vary the geometrical dimension, so I decided to change this parameter shown in figure. This is a simulation of the position of the electrons in transverse section of the beam with different delta x. I then verified them experimentally to see if the simulation were correct, and they will stand at the level of precision. Look at this image. On the upper graph you can see the electron simulated trajectory with the software, while under them there are the phosphor screen collected with the same simulation parameter. I guess the night spent trying to figure out how to use this ugly software were worth it, as there is almost no information online besides the fact that it's probably used at CERN. So if one would like to move the beam horizontally or vertically, this can be made simply by putting a pair of blades, like the one found in an oscilloscope, and then using a 4-quadrant power supply to move the beam around. So why spend a lot of time for this explanation? A normal textbook, they usually say that to have an electron gun you simply need a cathode and an anode at a high potential. And magically the electron will go past it indefinitely.
Electrons start escaping from the cathode and go to the anode, and because there is a hole at the center, they continue going forward.
But unfortunately this is a really inaccurate simplification, and I discovered this because my first experiment in electron gun didn't work at all. The fundamental factor ignored in textbook is the environment in which the electron gun is placed. As you can see from this animation, the electron gun made, well, like the one described before, would not work, because as soon as the electrons surpass the anode, they are attracted back towards it, and so they will strike a target with limited energy, and only if the target is close enough before the electron trajectory inversion in the direction. So instead, if you want the electrons to maintain their final kinetic energy, you need to have an environment in which the electrons travel to be at the same electrostatic potential as the anode. This is why the screen is in a TV is conducting by using a thin layer of aluminum and is placed at 30 kilowatts. Another way to get the same result is instead to have a grounded anode and the cathode at a lower potential, like in my design. With this system one can operate the environment at 0 volt. And this is the topology I use in my gun, and it has been chosen because my vacuum chamber must be at 0 volt, being made of metal and conductive. And also this gun is more versatile for different experiments. I also wanted to stress out the fact that this design differs from all the other homemade CRT electron gun, because usually the amateur uses a simple diode configuration, using an anode with a hole and not caring a lot about the geometry, and resulting in a lot of losses because the electrons go everywhere, because only part of the electron reach the target, while most of them hit the anode, conductor or wall of the chamber. But employing a lens system I can reach almost 100% efficiency of electron transfer from the cathode to the target, so that I have a much higher flux and control over the focused beam. So what about the high voltage power supply? I won't go much into details of how to build a high voltage power supply, because I've done that in this other video that you should definitely check out if you are radiation nerds like me. But if you want to have a general idea, the power supply is a simple flyback AC output with CV multiplier variable in potential from 3 to 20 kilowatt. We are limited in the volt range to the highest value before breakdown start to happen. Because amateurs are known to have a really bad vacuum system, this value is in the 10th of kilowatt range, if we are lucky. At a pressure of around 10 to the minus 4 millibar, it's okay for low voltage and might be reached with a high quality roughing pump, but a turbo is the way to go with this kind of experiment. Anyway, between the rubber gasket epoxy resin outgassing from my wear, I was limited in the 10 to the minus 5 millibar range. Even in this harsh condition, I could reach electron beam in the 15 kiloelectron volt range with some precaution, like surface finish and inter-electrode distance. This is a critical component to have a low light background and a high current flux. The cathode itself is a simple 12-volt halogen light bulb, with the top cut off. The light bulb itself is then placed inside this copper jacket that serves a different purpose. First of all, it prevents the electron from being ejected perpendicularly towards the wall, creating a conductive path that causes arcing. But also, this creates what is known as a crossover point, which is the point in front of the cathode where the trajectory of the electrons cross each other path. This particular point is very important because it makes easier focusing of the electron beam and acts as a virtual cathode. This copper cylinder also acts as a fixed Wanel electrode, which is the part normally found in CRT that is responsible with controlling the current of the beam by varying the potential applied to it. But instead, even the stem I played with geometry, and by having it at the same potential as the cathode, because they are physically connected, I varied the distance between the filament and the hole of the cylinder to have the desired crossover diameter and position and achieve easier focusing. The most important part of the cathode is the filament itself. In fact, the development of this component took me almost 1/3 of the time in this project, mainly because the information regarding it are almost impossible to find. I had to buy some book from the 40s to finally gather all the pieces together. This is because I wanted an oxide-coated cathode. This type of cathode employs a thin layer of metal oxide covering the filament to lower the work function of it, and achieving a higher emission at a lower temperature, increasing efficiency and lowering noise. I have been successful in making it work, and here you can see some comparison between the emission current between some of the cathode I tested. The intensity of the fluorescent screen light is proportional to the current carried by the electron beam at the same potential. On the left we have the bare tungsten wire and then an yttrium oxide coated cathode. And then finally you can clearly see a higher emission from the strontium one. A very important aspect to make this type of oxide-coated cathode work that we don't have time to discuss now is activation, which takes a dull and useless metal oxide into a wonderful emitter of electrons. During this process, part of the oxide is converted into the corresponding metal at the boundary of the filament due to the scavenger species present. This metal is a lower work function emitter like strontium, and being at a high temperature emit electrons by thermionic process, way more than tungsten does. During the activation process inside of the oxide layer, some channels are created that allow for ionic conductivity to kick in and enable the escape of the electrons from the surface where they are created. This process is extremely sensitive to poisoning from gas present inside of the chamber, and this is the reason why on amateur level this type of cathode cannot be easily achieved, at least in a dynamic system like mine, where I want to open and close the chamber often, because even after the slightest contact with air, the cathode needs to be reactivated. I was able to find the secret recipe used in this 1950s book that uses strontium and barium oxide and some other organic activating agent like nitrocellulose. I have yet to give the original carcinogenic formulation a try because I got good result even with my alternative, which consists in making a coating using a water suspension of finely ground strontium carbonate, then dipping it over the filament and letting it to dry with gentle heating in air. After that, the filament covered in strontium carbonate was inserted into the vacuum chamber, and after reaching the maximum vacuum, the filament was heated red hot by the current flowing. The emission increases as the activation proceeds. Unfortunately, it is really hard to measure temperature inside this type of system, and one should need an optical pyrometer. Activation is also aided by drawing some current from the tube, as the electron emitted probably help in reducing the oxide, shortening activation time. We can do some example experiment like cathodoluminescence, so collecting the light emitted by a material being hit by electrons. This is, for example, the cathodoluminescence spectra of the phosphorus screen I was using to measure the diameter of the beam. From this I was able to gather information about its chemical composition. In fact, each peaks come from an element present in the mixture. As you can see, it's a mixture of rare earth metal. We can also confront this with the spectra obtained by UV irradiation, and we can see a shift in the relative height of the different peaks. This results from the fact that extremely high energetic electrons excite every atom equally, while the less energetic UV irradiation only excites some of the energy level of the rare earth atom. Another experiment I performed is the creation of color center. These are point defects present in inorganic crystal lattice like this quartz, where some of the electrons we shoot at the material get lodged into the lattice and get stuck inside of an ionic vacancy. To do this, I simply placed this piece of fluorite in the electron beam path and irradiate for some minutes. We can verify the formation of F-center by heating the crystal after the irradiation. We should see this beautiful glow of the salt. This phenomenon happens because we are freeing the electrons from their trap, and during this process they decay into a more stable energy, releasing visible light that you can see. So now some conclusion. For now we have been able to develop an electron gun system at an amateur level, using simulation to create a specific geometry based on our needs. The simulated geometry was built with inexpensive crap and easily achievable by the amateur experimenter. I also showed you how it was possible to build a simple but effective lower function cathode employing oxide coating. There are countless other applications of this kind of apparatus that I want to explore in the future, like irradiating stuff with electrons that can induce interesting chemical reaction. Also, the critical aspect of cathode emission will be developed further by reducing temperature, and also I want to develop a novel type of electron emitter that doesn't need heat at all. So if you have any question, drop them down below in the comment, and bye.